Do aliens engineer planetary systems? Well, if they exist, which we don't know yet. We, humans, already know how to, let's say, create artificial islands. Now let's imagine a highly advanced civilization capable of much more. Why wouldn't such a civilization, instead of creating islands, build entire planets? Let's say they live in a system with one habitable planet. Traveling to another system takes a very long time. Meanwhile, the population is growing. So, instead of colonizing distant systems, why not just add a few more planets within the habitable zone of the existing system? For now, let's set aside the question of where to obtain those planets or the material to make them and how to actually move them around. Let's assume that our hypothetical civilization can accomplish all of this. Then another question arises. If we place many planets, dozens or even hundreds, within a habitable zone of a single system, will such a system be stable? Won't all the planets collide with each other, leading to a mega catastrophe? That we can actually try to figure out. How many planets can be in the habitable zone of one system? What is the maximum possible number of planets in general? Can there be a system where thousands of planets orbit just one star? Can multiple planets share the same orbit simultaneously? And how can one build a perfect, ultimate planetary system?
Let's talk about all this and more. My name is Andrei, and this is Cosmos Elementary.
Let's start by looking at our own solar system. It is currently quite stable. It contains 8 full-fledged planets, several dwarf planets, and numerous smaller bodies. There are still ongoing discussions regarding the definitions of dwarf planets and regular planets, which I discussed in more detail recently in a video about the Moon. For now, let's use the definition of planets according to the International Astronomical Union. So in the solar system, there are 8 major planets. So far, we have discovered more than 5,600 exoplanets, and several more thousands are awaiting confirmation. Perhaps among them, there are some systems with dozens of planets. Well, multi-planet systems certainly do exist. Some of you probably immediately thought of the famous TRAPPIST-1 system with its 7 planets. Our solar system for a long time held the record for the number of planets, and, well, it still does, almost. Currently, there is only one other known planetary system with 8 planets besides ours. That is the Kepler-90 system. This is a very interesting system. Looking at this comparison with our own solar system, it may appear quite similar. And there are similarities beyond just the number of planets. The star is similar to our Sun. Like in our solar system, the less massive planets are closer to the star and the giant planets are farther away. However, in this picture, the sizes are to scale, but not the distances. Actually, all 8 planets of Kepler-90 are located within 1 astronomical unit from the star. They are much closer together, and yet the system seems to be stable. This suggests that in theory, planets can be positioned much closer than in our system, and there could be more of them. Another conclusion we can draw is that we haven't discovered any crazy systems with dozens of large planets yet. Of course, in the known systems with 2, 3, 4, or even 8 planets like Kepler-90, there could still be undiscovered planets. So it is quite possible that we are still awaiting the discovery of some interesting multi-planet system. One more question. Are there any systems with multiple planets within the habitable zone? As far as we know, currently only one planet is known to be habitable in our solar system, and that is of course Earth. However, when the solar system was young, there might have been 3 potentially habitable planets. Besides Earth, both Mars and Venus could have been suitable for life. And even now, both planets are either within or very close to the habitable zone. Which shows that the zone itself, meaning the distance from the star where liquid water could exist on a planet's surface, is not the only factor. Even if we find planets at such distances from their stars, they could resemble Venus or Mars. But since we have very limited information about exoplanets, we can at least make some estimates based on that distance. Again, recall the TRAPPIST-1 system where 3 out of its 7 planets are located within the habitable zone. There have been theoretical studies suggesting that some systems could host up to 7 planets within their habitable zone. Another approach we will definitely use is placing more than one planet on the same orbit. There are various possibilities here. For instance, there could be a binary planet where two bodies of comparable mass orbit around their common center of mass at approximately the same distance from the star. As I mentioned in a recent video, an official definition for a double planet still does not exist. But in this case, it could be two bodies of comparable mass orbiting around their common center of mass. There are also several co-orbital configurations, such as horseshoe orbits. In my video about counter-Earth, I discussed whether another planet could be on the same orbit as Earth, but on the opposite side of the Sun. So could two bodies share an orbit? They could, and they do, even more than two. There are stable points in a system of two bodies known as Lagrange points, the most stable of which are L4 and L5. A third body or a group of bodies can occupy these points located at 60 degrees ahead and behind. In the solar system, obvious examples are asteroids, which are concentrated in Lagrange points of Sun-Jupiter system known as Greeks and Trojans. Similarly, analogous to Trojan asteroids, there could be Trojan planets. Theoretical calculations indicate that planets in certain systems could potentially reside in these points and share an orbit with another planet for quite a long time. However, unfortunately, we haven't discovered any co-orbital planets yet. There have been several candidates, such as Kepler-223 system, but subsequent observations revealed that it was an error and there are simply 4 planets on different orbits. But these are all either real observations or theoretical calculations that consider natural formation process. But we want to engineer a system ourselves, and that's a different story. The concept of this video came to me when I was messing around in Universe Sandbox, and there was a model of an ultimate planetary system. And then I came across an article on this topic that referenced calculations made by astronomer Raymond. And it turned out that he has a whole series of articles about creating systems with the maximum possible number of planets. A significant part of what I will be discussing further is based on his calculations, and of course I will leave links to all of his articles. And I also should mention that these are not peer-reviewed papers. However, in his calculations he used real scientific simulations that he employs in his main work. Moreover, many of these calculations are consistent with calculations from actual scientific papers. And Raymond is also the author of many scientific articles on related topics, including the evolution, architecture, and formation of planetary systems. Using the Kepler-90 system as an example, we have already seen that even around a star similar to the Sun, planets of comparable mass can be packed much more densely, not just in theory, but very much in practice. Are there any limitations on how close the orbits of planets can be? Well, it is obvious that you can't place them too close together, as the planets might collide, but even at a certain distance, the planet can still affect each other and destabilize orbits. There is a parameter called the Hill radius, or Hill sphere, also known as Roche sphere. Don't confuse it with the Roche limit, which is the distance at which a less massive body is destroyed when it comes too close to a more massive body. The Hill sphere, or Roche sphere, is a different concept. It refers to a distance from a body that is itself orbiting a larger body, within which the gravity of the smaller body dominates. For example, within the Hill sphere of a planet, smaller bodies will orbit the planet even while being influenced by the star's gravity. I've already mentioned Lagrange points. The Hill sphere is situated between the two Lagrange points L1 and L2. Let's calculate the Hill radius for Earth. It can be roughly calculated using this formula, where A is the distance from the planet to the star. In our case, it is 150 million kilometers or 150 billion meters. M is the mass of the planets. For Earth, it is approximately 5.97 times 10 to the power of 24. Capital M is the mass of the star. For Sun, it is approximately 1.99 times 10 to the power of 30 kilograms. We can quickly put it into Wolfram like this, and we get a result of 1.5 billion meters, or 1.5 million kilometers, or about 932,000 miles. Or of course you could simply type Earth Hill radius into Wolfram and it would give you the same result, even more precise.
But we never look for easiest ways.
So what does this result tell us? Well, we can immediately see that the Moon, which is approximately 400,000 kilometers away from Earth, is clearly within the Hill sphere. As I mentioned, the Hill sphere is situated between the Lagrange points L1 and L2, and the result we obtained is precisely the distance to these points. For example, this is also the distance at which the James Webb Telescope is currently located, and it is positioned at the Lagrange point L2. Everything aligns pretty well, but as we want to place a bunch of planets in our artificial solar system, what does this tell us? The example of Earth's Hill radius shows us that the distance is quite significant. Even though between Earth and the Moon you could fit all 8 planets of the solar system, although they would be packed very tightly, but the real question is how far apart the orbits of the planets need to be for these orbits to be stable. Clearly, if 2 planets, even of equal mass, are positioned so close that one falls within the Hill sphere of the other, a stable configuration is unlikely. They might collide, or one could even be ejected from the system. So there needs to be a greater distance between planets, ideally several Hill radii apart. Raymond references studies that show that minimum distance should be between 5 and 10 Hill radii for a system with multiple planets. If we reached a level of development where we could move planets or create planetary scale objects, and if we didn't want to travel to distant colonies around gas giants and preferred to stay within the habitable zone, how many planets could we place within the habitable zone of our solar system? It should be noted that even defining this zone is not that straightforward. There are various estimates for our solar system, ranging from conservative to more optimistic. I found this calculator for habitable zones, and here you need to input the surface temperature of the star. For the Sun, it is 5780 Kelvin, or approximately 5500 degrees Celsius, or almost 10,000 degrees Fahrenheit. You also need to enter luminosity. Since we typically calculate luminosity for other stars relative to the Sun, the luminosity of the Sun here would equal 1. The calculator tells us that in our solar system, the habitable zone starts at a distance of 0.75 astronomical units, which is 75% of the distance from the Sun to Earth, and ends at approximately 1.78 astronomical units. However, there's also a more pessimistic estimate, and in that case it is a much narrower strip, approximately in the region of 1 astronomical unit from the Sun. Judging by this image, Raymond apparently used values close to the optimistic estimate. He concluded that, considering the minimum required number of Hill radii, up to 6 potentially habitable planets could fit within our habitable zone. This is of course 6 times more than we have now, but it still doesn't sound very impressive. But I mentioned coorbital planets for a reason. We can at least double the number of planets by placing them 60 degrees apart in their orbits. In other words, one planet would be either at L4 or L5 point. This configuration could be quite stable, and with this approach, we could have up to 12 planets within the habitable zone of a Sun-like star. In these points, gravitational influence of 2 bodies on the third body is balanced out, which allows it to remain at these points for a long time. Some of these points are more stable, while others are less so. But having only 2 planets in the same orbit seems a bit boring. Can we fit more? Apparently we can. Here's a scientific paper that was published in Celestial Mechanics and Dynamical Astronomy journal. The authors of the paper conducted calculations and used simulations to determine how many planets can theoretically share one orbit, and here's what they found. According to their calculations, multiple planets of equal mass can share the same orbit under certain conditions. First, they must be distributed evenly around the orbit at equal distances from each other. The distance must be at least 12 Hill radii, and there must be at least 7 of these planets. But what is more interesting is that the maximum number is much higher. On Earth's current orbit, distributed evenly and at the required distance from each other, according to this article, you could fit 42 planets of Earth's mass. It seems almost unreal, but simulations show that such a configuration could indeed be stable on its own even over billions of years, provided there are no additional external influences. So in one ring there could be up to 42 planets, and initially we had 6 planets or 6 orbits. Is it possible to turn each of these orbits into such a ring? How far apart the orbits need to be depends more on the mass of individual planets, as it can affect other planets on neighboring orbits. According to this logic, increasing the number of planets on a single orbit does not significantly impact the distance between orbits. Raymond writes that within the habitable zone of a Sun-like star, it would be feasible to fit 6 rings, each with 42 Earth-mass planets. That makes 252 planets in the habitable zone. 252 potentially habitable planets around one star. But can we fit even more? The Hill radius and consequently the distance between orbits, as well as how many planets can fit in a single orbit in a stable configuration, depend on the mass of planets. Therefore, we can also try to manipulate the mass, since we are considering a hypothetical, artificially engineered system. If we increase the mass of the planets, fewer of them will fit. If we're talking about a planet with 10 solar masses, then within the habitable zone only 3 rings can fit, with 19 planets on each ring. That makes a total of 57 planets. However, if the mass is only 0.1 Earth mass, which is approximately the mass of Mars, then it is possible to fit 13 rings with 89 planets each. That totals 1,157 planets in the habitable zone. So far we've been talking about a Sun-like star. It's clear that if the star were different, the number of planets could also be affected. Less massive stars have smaller habitable zones, and consequently there would be fewer orbits. Fewer rings of planets could fit, and each ring might have fewer planets. So if we want to create a giant planetary resort, it's better to choose a star that is more massive rather than a red dwarf. But let's return to the case of a Sun-like star with Earth-mass planets. We found that we could have 6 rings with 42 planets each in the habitable zone. Is it possible to increase this number even further? Surprisingly, yes. The authors of the paper with the simulations about 42 Earth-mass planets previously proposed another interesting trick: retrograde orbits. In our solar system, all the planets, and not just planets, move in the same direction along their orbits. If you look at the North Pole of the Sun from above, the planets move counterclockwise. All the planets move in the same direction because they all formed from the same fragment of a molecular cloud, which had a preferred direction of rotation. When the Sun was forming, the remaining material created a protoplanetary disk that rotated counterclockwise. And the planets formed from the disk's material continued to move in the same direction. Once I've talked about gravity assists. This technique is used in spaceflight to accelerate or decelerate a spacecraft. In other words, the spacecraft's orbit can be raised or lowered. When a spacecraft flies close to a planet along a certain trajectory, the planet can transfer some of its angular momentum to the spacecraft, thereby accelerating it. Conversely, the planet can also take away some of the spacecraft's momentum, which would slow it down. And it depends on the spacecraft trajectory past the planet. Essentially, the planet either pushes or pulls the spacecraft, and although there is no direct contact between them, there is an influence through gravity. Something similar would happen between two planets if they were close enough to noticeably affect each other. When planets come close to each other while moving along their orbits, one can nudge the other. Over time, through many such encounters, this influence accumulates and the planets either come too close and collide, or they drift apart, and the configuration of the system changes drastically. That's exactly what I meant when I said that a system becomes unstable if the planets' orbits are too close. Another additional factor here is the amount of time the planets spend close to each other in their orbits. And how can we reduce this time? By making planets move in opposite directions. If two cars are moving in the same direction, one at a speed of 60 miles an hour and the other is overtaking the first one at 70 miles an hour, they will be close to each other for a certain amount of time. But if they were moving in opposite directions at the same speeds, so it's the same with planets. Moving in opposite directions, they would pass by each other more quickly and have less time to exert gravitational influence on one another. So by using retrograde motion, orbits can be placed closer together. If we arrange the planets on one orbit to move clockwise, on the next orbit counterclockwise, and then again clockwise, and so on, in the model made by Raymond within the habitable zone of a Sun-like star, we can fit not 6 but 8 rings, with 52 Earth-like planets on each ring. This would give us 416 potentially habitable Earth-mass planets around a single star. This model in the Universe in Box shows exactly this system, though I've exaggerated the sizes of planets to be able to see them better. Otherwise, it looks like this. We've already created quite impressive systems, but we've been limiting ourselves to the habitable zone, since we've allowed ourselves to imagine a hypothetical, super advanced civilization capable of constructing such systems. Would it be that strange to also imagine that they could create conditions suitable for life on planets even outside the habitable zone? So let's imagine that as well. But even so, we can't go completely wild. Stars in the galaxy can interact with each other and influence each other through gravity. In some areas of the galaxy, stars are much closer to each other, such as in the central regions, while farther from the center, the density of stellar population is much lower. Raymond uses a limit of 1000 astronomical units from a star. Within this radius in our region of the galaxy, interaction from outside the system, if they occur at all, would be extremely rare. Here, the distance between the rings needs to be gradually increased, and eventually this area can accommodate 57 rings with 42 Earth-like planets. That's 2,394 planets. By the way, when we see such crazy numbers and images, a few questions might arise. Of course, in these illustrations, the sizes of planets are exaggerated for clarity. In reality, they would need to be smaller. So we've been discussing the stability of such planetary rings, but if we start placing thousands of planets around a star, won't these planets end up outweighing the star itself? Even though 2,394 Earth masses is more than combined mass of all 8 planets in the solar system, it is still far less compared to the mass of the Sun. The Sun is approximately 333,000 times more massive than the Earth. The second question is where to get so much material. We can make some estimates, again looking at our own solar system as an example. Planets form from the leftover material that did become the part of the star's mass. And these leftovers are relatively small. The Sun accounts for 99.8% of the mass of the solar system. All the planets, moons and smaller bodies fit into that remaining 0.2%. To find out how many Earth masses we have, it's relatively straightforward to calculate. The mass of moons, dwarf planets, asteroids and comets can be ignored as their combined mass is negligible, compared to that of the major planets. In fact, even the masses of Mars and Mercury can be disregarded, with their 0.1 and 0.06 Earth masses respectively. The mass of Uranus is 14.5 Earth masses, Neptune is 17, Saturn 95, and Jupiter 318. Adding these together gives 498.5 Earth masses. Adding Earth and Venus brings the total to approximately 500 Earth masses. If we use our system as a reference, we definitely don't have enough material for 2,394 planets. However, for the 416 planets we wanted to place within the habitable zone, it seems that there is enough material. So our extraterrestrials would just need to dismantle their planets and reassemble them into Earth-mass planets within the habitable zone. No big deal. But here's the problem. Earth-like planets consist of heavier elements, with significant portion of Earth mass being iron and various silicates. In the mass of our solar system, these elements make up only a small fraction of its total mass. In fact, throughout the entire universe, the majority of ordinary mass consists of two lightest elements, hydrogen and helium. Specifically, 74% of all matter is hydrogen and 24% is helium. Yes, in planets, especially in rocky planets, given their formation history, the proportions differ. But the bulk of the mass of all planets are gas giants, and Jupiter and Saturn are primarily made of hydrogen and helium. In short, there's clearly not enough heavy elements in our solar system to create over 400 Earth-like planets. Perhaps in another system there might be more suitable material, Or our hypothetical extraterrestrials could bring the material needed to construct planets from other systems. In his articles, Raymond also presents examples of truly insane systems. If you reduce the mass of the planets and use the mass of Mars, you can fit 121 rings with 89 planets each within the radius of 1000 astronomical units, totaling 10,769 planets, and with the mass of the Moon, 65,000 planets. Of course, while these scenarios might be stable in simulations, real life is much more complex. Even if our hypothetical civilization could somehow build a system of 416 Earth-like planets, and it could be stable for a long time, there are many factors in the real galaxy that could disrupt this stability. A nearby star approaching too closely, a wandering planet passing by, a neutron star or a black hole, a denser cloud of gas and dust in the path of the system within the galaxy, and so on. But it is still intriguing to theorize about the limits of what might be possible. And of course, the views on the surfaces of planets in such systems would be epic. Stripes of bright planets in the night sky. Nothing like that could form naturally. And although we haven't found any extraordinary planetary systems yet, it doesn't mean we won't discover them in the future. And even if there aren't hundreds of planets, we might still find unusual, interesting configurations that differ from our solar system.
Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe. Bye!